Construction of the Rhine Bridge hard. A structural feat across the Rhine Bridge hard in Austria, connecting Hard and Weißach, is a monumental project that underscores advanced engineering and flood management considerations. Initiated to replace an outdated structure, the new bridge is designed to optimize traffic flow, improve flood discharge, and meet modern standards. Spanning approximately 255.6 meters with 4 spans of 50 meters, 125 meters, 50 meters, and 31.6 meters, the bridge's construction demonstrates a blend of precision engineering and state-of-the-art techniques. Here, we delve into the intricate phases of this project and the engineering marvels that bring it to life. Initial preparations and setting up the construction site commenced in June 2020 with groundwork to establish the assembly site. Given the Rhine's seasonal flooding, it was crucial to carry out much of the work during periods of low water discharge in winter. By September 2020, significant strides had been made in constructing the substructure on the Rhine's foreland. This substructure forms the base for the bridge's pillars, facilitating the load-bearing capability essential for a steel composite bridge designed to withstand increased river discharge. The early stages included the creation of auxiliary supports on the Weißach side, which were essential for stabilizing the structure during initial phases. By the end of October 2020, these supports were ready, enabling the next stages in the steel construction process. In November 2020, prefabricated steel components began arriving at the site from production plants in the Czech Republic, Hungary, and Austria. The philosophy behind the project was to fabricate the largest possible segments off-site, reducing the need for numerous transports to 66 specialized deliveries. Some components weighed up to 90 tons, necessitating careful logistics and coordination. The bridge's design uses a steel-concrete composite structure, integrating 2 trapezoidal steel box girders with a reinforced concrete carriageway slab that would be added later. The steel segments were assembled on the west side of the Rhine, where they were welded. Most of this welding was done manually, employing gas-shielded welding techniques, while the longitudinal seams on the top face were welded with submerged arc welding, a highly effective method for producing robust, durable seams. Given the bridge's operational demands, weld joints underwent rigorous preparation and post-treatment to ensure durability. This process included grinding the seams and then sandblasting, followed by the application of protective coatings to shield the structure from environmental elements. The bridge's construction employed the incremental launching method, a process of systematically assembling and advancing the structure section by section. In early 2021, this method was applied to the 2 steel box girders. The segments were joined, reinforced, and then pushed across the pre-existing substructure, progressively extending the bridge over the Rhine. The first incremental launching phase began in February 2021, using 4 hydraulic presses capable of exerting a combined force of 240 tons. The procedure involved 10 attachment phases and 10 shifting phases, with each shift covering lengths from 6 to 45 meters. During each cycle, additional steel components were attached to the previously assembled sections, slowly forming the bridge in its intended position. A project of this scale requires stringent quality control to ensure the steel structure can withstand environmental pressures and long-term wear. Each weld seam was inspected with ultrasound to detect potential defects that could compromise structural integrity. The coating application process, another critical phase, was conducted in accordance with strict guidelines to prevent corrosion and maintain durability. Only approved materials were used for this process, ensuring compliance with high-quality construction standards. In June 2021, the steel box girders were pushed across the Rhine's central channel for the first time. This stage marked a significant milestone, reflecting the complexity and precision required for the bridge's construction. The incremental launching process subjected the bridge to changing stress patterns, influenced by factors like solar radiation, temperature variations, and wind. Engineers and specialists monitored these variables closely, as well as potential ground settlements, to address any unexpected shifts in structural integrity. The Rhine Bridge hard's design is not only functional but also architectural. The bridge's main span is supported by a harp-shaped cable structure anchored by pylons rising approximately 12 meters above the river. With a low mast height, this cable arrangement optimizes stiffness while maintaining a low visual profile, blending into the surrounding environment. The cable's shallow inclination helps distribute loads evenly, creating an aesthetically pleasing and structurally sound framework. The bridge's steel masts, with their rectangular steel box cross-sections, lend a sleek, modern look to the structure while ensuring optimal load distribution across the river piers. This attention to both engineering and design highlights the bridge's dual function as a transportation route and a flood management solution, ensuring resilience against increased discharge from 3,100 cubic meters per second to a projected maximum of 4,300 cubic meters per second, HQ 300. After the steel structure's successful positioning in October 2021, further work continued to complete the bridge. In 2022, the reinforced concrete deck slab was added, marking the near completion of the bridge's superstructure. Additional work focused on reinforcing the structure through a series of stiffening measures, optimizing its resilience to traffic and environmental factors. The Rhine Bridge Hard is a testament to engineering innovation, combining advanced construction techniques, environmental resilience, and meticulous planning to achieve a structure capable of meeting modern demands. It symbolizes not only a practical infrastructure upgrade, but also a forward-thinking approach to flood management and transportation efficiency in the region. The bridge's complex construction phases, from incremental launching to precise welding and bracing, underscore the expertise required to realize this ambitious vision. Upon completion, the bridge will enhance connectivity and resilience, providing a lasting solution to the challenges posed by natural forces and evolving transportation needs. Its success showcases the capabilities of contemporary engineering to harmonize form and function in the service of communities and environmental sustainability. Following the project's initiation in 2011, the Nissibi Bridge was designed to be a cable-stayed suspension bridge with a single central span, a unique and complex design choice for the region. What truly set the Nissibi Bridge apart was that it was entirely designed, constructed, and managed by Turkish engineers and workers, making it a fully domestic endeavor. This accomplishment marked a new chapter in Turkey's civil engineering, showcasing the country's growing expertise in large-scale infrastructure. In 2012, Gulson Holding, which had secured the contract, commenced construction. The project began with a major excavation phase involving the removal of over 150,000 cubic meters of rock and limestone to lay the foundational support for two 96-meter-tall pylons on either side of the bridge. The pylons were built with C60 high-strength concrete and reinforced with 4,200 tons of steel rebar, enabling them to withstand seismic events, an important consideration due to the region's earthquake-prone environment. The pylons were engineered to endure significant seismic activity, with the ability to withstand earthquake forces, expected over a 2,475-year recurrence period. Following the project's initiation in 2011, the Nissibi Bridge was designed to be a cable-stayed suspension bridge with a single central span, a unique and complex design choice for the region. What truly set the Nissibi Bridge apart was that it was entirely designed, constructed, and managed by Turkish engineers and workers, making it a fully domestic endeavor. This accomplishment marked a new chapter in Turkey's civil engineering, showcasing the country's growing expertise in large-scale infrastructure. In 2012, Gulson Holding, which had secured the contract, commenced construction. The project began with a major excavation phase involving the removal of over 150,000 cubic meters of rock and limestone to lay the foundational support for two 96-meter-tall pylons on either side of the bridge. The pylons were built with C60 high-strength concrete and reinforced with 4,200 tons of steel rebar, enabling them to withstand seismic events, an important consideration due to the region's earthquake-prone environment. The pylons were engineered to endure significant seismic activity, with the ability to withstand earthquake forces, expected over a 2,475-year recurrence period. Engineering challenges and innovative solutions. The Nissibi Bridge's construction process presented numerous engineering challenges. A key feature of the bridge was its use of approximately 6,500 tons of structural steel, equivalent to what would be required to build a full-sized replica of the Eiffel Tower. The steel sections, each weighing 250 tons, were manufactured in Osmaniye and transported to the construction site in segments via specialized trucks. To support each segment, the bridge incorporated 80 steel cables ranging in length from 67 to 217 meters, providing stable and balanced support throughout the span. A particularly challenging aspect of construction occurred in 2014 when water levels in the dam reservoir unexpectedly dropped, causing pontoons used in the construction process to become grounded on dry land. Rather than waiting several months for water levels to rise, the engineering team devised an innovative solution. They extended a supporting beam by 17 meters, effectively bypassing the need for water and allowing the load to be stabilized. This creative approach prevented a potential year-long delay and significant additional costs, ensuring that the project remained on schedule and within budget. Throughout construction, maintaining the bridge's structural integrity was of utmost importance. Engineers conducted daily monitoring of the bridge site, measuring variables such as temperature, wind speed, humidity, and seismic activity. The meticulous monitoring ensured that the bridge could withstand the local environmental conditions and would maintain safety standards even in extreme weather or seismic events. The construction team faced additional challenges with temperature fluctuations, which varied greatly throughout the day. Engineers compensated for these temperature changes by measuring ambient conditions every hour and making necessary adjustments. For instance, the bridge's structural components were calculated to shift by up to 10 centimeters during the day due to these temperature changes, a factor engineers took into account in real time to maintain the bridge's alignment and structural soundness. The bridge also integrated advanced structural monitoring sensors, which continue to provide real-time data on temperature, humidity, wind speeds, and seismic accelerations. These sensors play an essential role in ongoing maintenance and safety, as they enable engineers to remotely monitor the bridge's status and respond to any potential structural issues before they escalate. The final stages of the Nissibi Bridge's construction took place in 2015. During this phase, the last steel segments were lifted into place, and final adjustments were made to the bridge's cable stay system. Each segment required careful handling and coordination. Engineers used specialized heavy lifting equipment designed by Gulson Holding to secure segments weighing up to 250 tons. After lifting each segment, workers meticulously aligned and welded the components together, a process that could take up to a week per segment due to the precision required. The last segment was lifted into place in the summer of 2015, marking the completion of the Nissibi Bridge's primary structure. After nearly 3 years of planning, construction, and overcoming obstacles, the bridge was ready for its official inauguration. What made this accomplishment even more impressive was that the project was completed without any major safety incidents or environmental issues, making it a model for future infrastructural projects in terms of environmental responsibility and worker safety. Since opening in May 2015, the Nissibi Bridge has transformed transportation and regional connectivity in southeastern Turkey. By re-establishing the connection between Sivrik and Kata, as well as linking Adıyaman, Diyarbakir, and Şanlıurfa, the bridge has revitalized social ties and significantly boosted regional trade and tourism. The time and cost savings achieved by eliminating the dependency on ferries have positively impacted local businesses and enhanced the quality of life for residents in the region. The Nissibi Bridge stands as a landmark not only in Turkish engineering but also in regional development. It serves as a reminder of Turkey's increasing capability in large-scale infrastructure and its commitment to using domestic resources and expertise. As the first suspension bridge entirely built by Turkish engineers and workers, it has set a precedent for future projects in Turkey and is expected to inspire similar infrastructural initiatives. The Nissibi Bridge is much more than just a physical structure. It embodies Turkey's progress in civil engineering, its dedication to regional connectivity, and its capacity to overcome complex logistical and environmental challenges. The bridge has redefined the landscape of southeastern Turkey, both physically and economically, bridging not just bodies of water, but also communities, cultures, and economies. For Turkey, the Nissibi Bridge is a symbol of pride, resilience, and a commitment to a connected future. The construction of the new Brunsttobel Bridge over the Weißach River represents a remarkable feat of engineering, technical innovation, and logistical planning. Situated along the L4 Doriner Strasse in Austria, this bridge was initially built in 1939. Due to war damage in 1945, it was partially reconstructed and reopened for traffic in 1949. Though strengthened in 1979, a recent inspection highlighted serious structural deficiencies, prompting the need for a complete rebuild. Given the importance of this route for regional traffic, engineers face the challenge of maintaining vehicle flow while enhancing safety and meeting modern standards. The final design, implemented by Scheimetter Consult and constructed by Wilhelm and Mir, yielded a durable, modern structure that retained accessibility during construction. The new Brunsttobel Bridge, designed as a three-span pre-stressed concrete structure, stretches a total of 127 meters across the Weißach. Its spans measure 38 meters, 51 meters, and 38 meters respectively, accommodating varying load requirements and minimizing the environmental footprint in the riverbed. The bridge's cross-section is a slab beam with a variable height of 2 meters at midspan and 3.5 meters over the piers. Its total width is 10.5 meters, allowing ample space for two-way traffic while ensuring structural stability and load distribution. To improve traffic safety, the approach ramps were realigned, providing a more streamlined entrance and exit to the bridge. This design minimizes sharp turns and blind spots, reducing the risk of accidents and improving visibility. The bridge piers were strategically positioned on the steep banks flanking the Weißach, enhancing stability by anchoring the structure into the rocky terrain rather than the softer riverbed. This design choice also reduced the bridge's vulnerability to flooding and erosion. One of the primary construction challenges was accessing the steep wooded slopes along the river. To reach the pier locations, a temporary construction road was built along both the left and right banks of the Weißach, allowing heavy machinery and materials to be brought to the site. The piers required deep foundations to counter the risk of scouring by the Weißach, necessitating the use of 9-meter deep caissons constructed in sprayed concrete. These caissons, reinforced with dual layers of rebar, were secured into the bedrock, ensuring a stable base immune to river-induced erosion. In particularly steep sections, excavation stabilization was required to prevent landslides. To achieve this, geotechnical engineers installed anchor systems with injection anchors and applied 2 layers of reinforcing steel mesh covered by 20 centimeters of sprayed concrete. This process stabilized the excavation sites and ensured the surrounding terrain remained secure during construction. Due to the ambitious project timeline, construction progressed through winter. Cold weather presented challenges for both labor and material integrity. However, contractors managed to complete the foundations for both piers by February, allowing the team to advance into the next construction phases without delay. Prefabricated rebar cages were constructed on the ground and then lifted into place using cranes, streamlining the installation of reinforcements for each pier section. The formwork was designed to climb as the concrete was poured, allowing each section to be completed consecutively within 2-day cycles. To handle the load from the bridge's decking and formwork during construction, a massive scaffolding structure weighing 900 tons was erected. This framework was built in stages, with individual truss components assembled on-site and jacked forward using cranes. The scaffolding's design allowed it to support up to 3,000 tons, accounting for the weight of the bridge itself, formwork, and materials during construction. Once the scaffolding was in place, work on the deck began. A modular formwork system was used, allowing pre-assembled sections to be lifted and precisely positioned. This minimized on-site adjustments and facilitated efficient concrete pouring. The deck was constructed in multiple phases, starting with the side spans and concluding with the central span. This staged approach allowed each segment to be secured, ensuring overall stability while minimizing potential structural shifts. The bridge's pre-stressing process involved inserting and tensioning cables through conduits embedded in the deck. The cables were gradually tightened to a load of 230 tons per bundle, stretching up to 75 centimeters in length. This pre-stressing technique significantly increases the bridge's load-bearing capacity, distributing forces more evenly across the structure and ensuring durability. With the deck complete, workers installed drainage systems to manage rainwater runoff and prevent water damage over time. The roadway layers consisted of a 40-centimeter unbound base layer and a 20-centimeter upper base layer, followed by a 14-centimeter bituminous layer and a final 3-centimeter asphalt concrete surface. This final layer provides the necessary traction and durability for vehicle traffic, and its seamless installation, completed over 2 nights with road closures, ensured the smoothness and longevity of the roadway. The approach ramps on either side of the bridge presented unique challenges. On the Krumbach side, the road had to be elevated by up to 5 meters, necessitating the construction of a 60-meter-long retaining wall to support the elevated terrain. Micropiles were installed to secure this structure, while additional reinforcement ensured stability on the Doran side, where a 50-meter-long stone wall and an anchoring system were required to prevent rockfall. After the new bridge was operational, the old structure was carefully dismantled. The removal process began with the deck's asphalt layer, followed by the steel-reinforced concrete deck. Special attention was required to maintain stability during this phase. Steel components of the old bridge were divided into sections, lifted out with cranes, and transported off-site. The remaining columns were anchored with steel cables before being dismantled and removed. Following the demolition, environmental restoration work commenced in October 2015. The riverbanks and surrounding areas were stabilized and revegetated, returning the Weißach landscape to its natural state. By late 2015, the project was complete, meeting both timeline and quality objectives. This success was attributed to the collaborative efforts of engineers, contractors, and local authorities who meticulously planned each phase and adapted to challenges efficiently. The Brunsttobel Bridge project serves as a prime example of modern bridge engineering, combining innovative design, planning, and advanced construction techniques. The project addressed structural deficiencies while preserving traffic flow and enhancing safety on the L4 Doraner Strasse. Each aspect, from foundation work to pre-stressing and road surfacing, was carefully executed to ensure long-term durability and environmental compatibility. The successful completion of this project not only underscores the importance of technical precision and teamwork in civil engineering, but also highlights the impact of infrastructure on regional connectivity and safety. The Brunsttobel Bridge stands as a resilient, modern structure, poised to serve the community for decades to come.